Okay. All right. So he's apparently not with us right now. And is there anybody who I might have missed? Okay, excellent. So we got everybody covered, ready to jump into the program. Looking for any comments or whatnot. We're good. Okay, so so you're looking at the screen titled Hydrostatics, Hydrodynamics. There are about 120 slides, and we kind of start off a little bit slow. We cover a lot of theory, concepts, and principles, basic stuff, fundamental stuff initially to get everybody warmed up. Cover units, which are very important in the application of equations and solving or analyzing different kinds of hydrostatics, hydrodynamics problems or situations. So we'll start off slow with all that, and then we'll get into what we call case studies. It's basically that look like problem examples, that sort of thing, and we'll work those. And initially we'll kind of again try to crawl before we walk. And meaning we will start off some of the case studies and problems in hydrostatics and hydrodynamics by taking a simplified, ideal kind of approach, meaning we try not to take into account the losses and so forth initially, so that we can kind of get our arms around the basics a little bit easier and quicker. And once we've kind of warmed up on all of that, then we later on in the program, in the latter half of the program, we start bringing the losses into consideration, and we let the things get more complex and so forth. So basically get into more intermediate level hydrostatics, hydrodynamics type of analysis. So that's how we kind of work our way through from the more fundamental stuff to the intermediate level, so to speak. So that's how the program will progress. So if you see us, looking at things in what might appear to some of you who already have some background in hydrostatics, hydrodynamics, as overly simplistic or whatever, just bear with us. That's just the initial, laying the foundation straight, and then we'll basically get into into more complex kind of scenarios and bring in some of the non-ideal kind of parameters or metrics into the overall consideration. So as when we talk about fluids, fluids can be gases or liquids, and when we consider liquids in this program, they're assumed to be incompressible. When we talk about gaseous fluids, such as air or other types of gases, we're obviously going to assume them to be compressible. And also you'll see that when we get into the gaseous realm, you can analyze gases as ideal gases or non-ideal gases, and we'll get into the differentiation or distinction between the two. Obviously, if you consider gases ideal, then it opens up more doors for you in terms of availability of more equations, more tools to be able to analyze those particular situations that have those that involve those ideal gases. While in a non-ideal gas scenario, you will not be able to use the ideal gas equations, and you'd be basically you'll have fewer tools at your disposal. So that's kind of how that works. Stephen, I see you've just joined us. I see your camera just popped up, which you can turn off if you'd like, and there you go. But welcome. We just got started. You haven't missed much. If you can hear us, just acknowledge that you're there so I can mark you present.
I'm here, thank you.
Okay, good deal, excellent. So, so bottom line, an example of what I'm saying, a very kind of a simple example would be where if you look at water, at when the water vapor is in saturated vapor state, these different phases of substances, particularly water, where you start from subcooled. Some could say, well, start with supercooled, but we don't go that far on the lower end, but starting from subcooled all the way up to a superheated vapor, as you examine the different phases of water, which we do in our thermodynamics program, which I think we have scheduled in January, if I'm not mistaken. So as we look at the different phases of water, which is just one example here, when you look at H2O and in saturated vapor form, where it may be all vapor, it's not ideal gas. That's not considered ideal gas. You would have to convert it to essentially superheated vapor, meaning raise its enthalpy substantially beyond the saturated vapor line on the typical temperature enthalpy graph. You'd have to get past that point and drive it into the superheated realm for it to be treated as basically an ideal gas. And really, the air we breathe basically is it's superheated air, superheated gases that are in superheated phase. Why? Because in order for them to become saturated vapor or liquid, we'd have to drive the temperature way down and raise the pressure substantially, and that is way beyond the well below that kind of temperature would be well below the STP temperature. Pressure would be much higher than the STP pressure. Certainly totally abnormal conditions, but under normal room temperature kind of conditions, the air we breathe is indeed, you might say, superheated and therefore ideal gas. So you kind of look at the superheated and ideal gas kind of in an interchangeable fashion in that manner. So again, that's something we get into more in our thermodynamics program. Okay, so gaseous fluids we're going to consider and assume to be compressible. All right, when we talk about fluid pressure, the pressure is defined as force per unit area, and it in the U.S. unit realm, which is also called the U.S. customary unit realm, which is really the imperial unit realm, which is the British unit system. You would typically measure pressure in pounds per square inch or pounds per square foot in the U.S. unit system. So really, fluids is part of mechanical engineering. That's the way I view it. If somebody disagrees with it, you have a different perspective, please chime in. But it's part of mechanical engineering, and mechanical engineering is really one of those disciplines in engineering where I think we are pretty much still, in most cases, the analysis are done in U.S. customary units. That doesn't mean that's always the case. In some cases, people prefer to, use metric unit system or SI unit system equations. But either way, you just need to make sure that the equation you're using is designed or stated in the unit system that you're about to use. So bottom line, mechanical engineering realm is one of those realms where in the U.S. a lot of the analysis in engineering is conducted in U.S. units. Now you leave the United States, go to most of the rest of the world, people have pretty much switched to the metric unit system, and therefore if you are talking about pressure, in Europe, for example, and even in UK, they've kind of I would say more than 50% converted to the metric unit system, and on their way to full conversion. So bottom line, if you go to Europe, go to Canada, same thing. Canada, although they'll recognize our U.S. units, you see that they're also pretty much on their way to full conversion to metric unit system. So pressure in the metric unit system would be measured in pascals, and 1 pascal is essentially also defined as 1 Newton per meter squared, and we are going to do some calculations through the course of the day in metric unit system as well. So So that's just a little clarification. Now, if you're wondering, hey, what is a Pascal relative to the 14.7 psi atmospheric standard atmospheric pressure? Well, 14.7 psi a standard atmospheric pressure is basically equivalent to 101.3 thousand pascals, or 101.3 kPas. So there you see the statement of different of atmospheric pressure in various units. 1 atmosphere, 14.7 psi, and inches of water column, it would be a little over 400. And we'll actually illustrate how that is arrived at. This when we say that atmospheric pressure, mean sea level atmospheric pressure, is about 400 inches of water column, or how do they come up with that? And once you understand how that, and that's through a very, very simple example, I think you'll find that interesting. And then once you see that, then you can also explain how they come up with 29.92 inches of mercury column sustaining 1 atmosphere. Or for that matter, 760 millimeters of mercury as well. So you can see how some of these parameters are arrived at. Very, very simple kind of illustration, mathematical illustration of that. We'll cover that in a bit. So the other very important takeaway from this slide is the mathematical statement or definition of absolute pressure. And that's this equation, through this equation. So absolute pressure is a combination or sum of gauge pressure plus the atmospheric pressure. So really, there are some books, and then when you took your PE exam, you may remember the old EIT book by PPI, Professional Publishing Incorporated. And their yellow EIT book used to have a little a diagram in there. For some reason, it stuck with me over the many years, where they kind of illustrate through a little picture or diagram of a gauge, and they show you how the typical gauge pressure is indicated with a steam gauge, quote unquote, pressure indicator, not the fancy dancy new transducer electronic, transduced electronic indicators of pressure. You see how it's kind of spring based. So the tube that turns into, it coils up into a spring kind of a formation. So as you pressurize that tube, you end up basically uncoiling or coiling, any way you want to look at it, that mechanism which moves the dial or the needle.